Hey, Phil.
Hey, Christian.
Thank you for joining me on this call. We're going to be talking about design of experiment. I do follow your hashtag DOE by Phil K on LinkedIn. What we're trying to do with these kind of videos is I wanted them to be as authentic as possible, so you don't know why you're here.
No.
So there's three possibilities we can talk about, and you get to choose. So the one thing we can talk about is someone reached out to me on LinkedIn and said he wants to have a specific design of experiment where he has some continuous factors, some categorical factors in a blocked run. Another is that someone wants to have a definitive screening that we then realize is not enough, kind of a sequential design of experiment thing. And then the third possibility is if you knew everything you know today about the content there is about design of experiment, but you don't know anything about design of experiment other than it exists. Like, how would you go if you were, let's say, a engineer in bio or biostatistics, and you want to get started with design of experiment? How would you go about that? It's a big question.
That's a big question. Yeah. So I think that, they're all really good questions. The last one's a big question. So I'd probably want to think about that a little bit more. The second one's really good because I don't think enough people think about sequential design of experiments, and too often we present design of experiments and definitive screening designs as like a one-shot thing, whereas really it's about a sequence of learning. I'm very guilty of that. So I think that would be a nice thing, but probably the easiest thing to tackle now would be that question number one. I'd love to have a
I was hoping for that one. Yeah. Okay, so option number one, I found the requirements sent to me. I have my jump open. They were kind of smallish, but what it says is, again, it's 2 continuous factors at 3 levels, 2 continuous factors at 4 levels, 2 categorical factors with 2 levels. Right. So like a binary yes/no response. We want to test main effects, some second order interactions, and we want this to be in less than 30 runs, done in 3 blocks, as one of the first one here are hard to change. So let's assume it's like a temperature, and it's difficult to change the temperature as it'll have like a long layover.
Right.
And then less than 30 runs, and we need the power to be more than 0.80.
Okay.
But those 3 things really stick together, right? Like the amount of runs with the power.
Yeah, that's where it gets interesting, definitely. I think it's, even without that, it's probably quite interesting anyway, but it definitely gets interesting with those last 2 requirements,
Yeah. So where do you want to start?
Well, so the first thing to start is to say, this is not going to be a textbook design. It's not a definitive screening design. They're great, but this doesn't fit into the plan of a definitive screening design. So we're going to be going to custom design from the DOE menu in Jump.
So I go to DOE and custom, because this is a pretty custom. Like, you go into the shop and say, I don't want that bike, I want this bike, and you like explain the bike you want. It's like, okay, I can get that to you, but it's not on the shelf.
Yeah, these are some bespoke requirements. Flat handlebars, disc brakes. I don't know. I'm trying to think of a bespoke bike. My bike's pretty textbook, but So custom design is at the top of the DOE menu in Jump because it's the most flexible. And I think this is one of the things I've heard recently is people telling me that design of experiments is a very rigid methodology. And I just think that's complete rubbish. It's really flexible. Modern design of experiments is really flexible to what you need to do with your experimental objective.
Yeah, so what I do here is I sometimes says, I really don't care what your response is. And people get taken a little back by that because that's really the most important thing. But for the sake of this kind of experiment, it's not like at this stage, it doesn't really set anything for a design. Is that correct?
Yeah, it's right. If you're doing the experiment, you definitely need to know what your response is. You really need to think about what your objectives are of your experiment. And you need to be confident that you can measure that thing, this output, this response, reliably, accurately, precisely? You know, if you just ran the same conditions 10 times, do you get more or less the same result? Because if you're getting very variable results when you don't even change any factors, then you can kind of forget about doing an experiment. You're not going to learn anything. So it's really important, but absolutely for the purposes of designing the experiment, what we put in this bit doesn't make any difference.
You said something interesting there, Phil, and it's not the context of this video, but your measurement system is important when we thought about design of experiment. It's just not as sexy as design of experiment. You gotta be honest there. But a lot of people say, well, I'll just do every run 3 times, and then I kind of understand my measurement system while I'm doing the design of experiment. But I try to say to people, understand your measurement system, then do a design of experiment. Well, what would you do? Like do repeated runs or take the two things apart?
It kind of comes down to what you know about the process and the measurement process, like how good they are. If it's a process that you've been running like loads of times already, you already just kind of know through experience that you can measure it reliably, then maybe you don't need to do a lot of work. But if it's something very new, or if you've got a lot of concern about whether you can measure this thing reliably, then definitely invest some time in it. I can remember an example in industry where I was helping out doing a designed experiment on a process, and the results of the whole thing came back. You know, we'd spent a couple of weeks doing the experiment, and there were 3 repeat runs within the experiment, and the response was on a percentage scale. And the 3 repeat runs, same factor settings, the range of answers we got for those 3 repeat runs were between like 20% and 80%. So it was just all over the place. And it just turns out we just couldn't measure the thing, the outcome that we cared about in any way repeatedly, or, you know, and we didn't really have control of the process. So we didn't learn what we wanted to learn. We learned that basically the problem was the control of the measurement process there, which was, you know, useful to know that, but we could have found that out before we did the big experiment.
You could just have done those 3 repeated runs in the beginning, then realizing I can measure this, and then not do the design of experiment.
But hey, so if you're not confident that you're going to be able to measure your response reliably, then invest some time doing that before.
Or if you're unsure, like you just said, like do 3 repeated runs, see what comes out. If it's fairly consistent, you're good.
Totally.
That would be like a low bar, and I like low bars. All right, so we have something important as a response. Let's start putting in some factors. So we're not going to give these names. I'm not that good at just figuring out names as I go. So that's going to be a total of 4 continuous factors.
Right.
So in custom design, this is not where I select how many levels, correct?
Well, it depends. So we can specify factors as discrete numeric. So if they've got, you know, I'd be interested to know why some of these factors are at 4 levels. So you've got one there, where we can actually specify what the 4 levels are. I mean, maybe you've got an oven that only has 4 temperature settings. You can't
1,
set it
2,
any
3, 4. Right?
Exactly.
That would be discrete numeric, right?
Yeah, totally. Yeah.
So so could we say that if you, for some reason, you want to have it 4 levels, fine, that's okay. If you are free to define what these 4 levels are, it's a continuous factors. If you are somehow constrained to defining, let's say you have pH and you get them at 4 different levels of concentration, it's a continuous variable, but it's discrete numeric in the sense that you don't decide the levels of pH.
Yeah, you know, maybe you're buying in already made up buffer solutions with fixed pHs, and you can get one that's 7, one that's 7.5, one that's 8.2. That would be an example of something that's discrete numeric. It's a numeric factor. You know, theoretically, it could take any value between 1 and 14 if it's pH. But the actual settings that you can execute on are discrete values.
Are limited to what you can actually put in your basket when you shop online.
Right. Yeah.
We're going to be assuming that, for the sake of simplicity, that they can set it at any level. All right. So that means, since it's not discrete numeric, I choose later on how many levels I wanted it.
Yeah, we'll decide the number of levels. That's going to be defined by the model that we say that we're going to estimate.
We'll get to that just in a minute.
Yeah.
The last thing we need to do at this stage is add the two categorical factors at 2 levels.
Yeah.
So that'll be like a yes and no.
Mm-hmm.
And this will also be a yes and a no. So those are pretty common.
Yeah.
So not much there. So that's the 6 factors that was asked for. So if I hit continue, this is a place where I get a lot of questions like, what is happening here? And the way I try to explain this is what you're looking at is the equation you want to look at or define with the design experiment. But right now, this equation has a y. So something important, then it has an intercept with where you cut the b, and then it has 6 main effect factors. Is that kind of correct?
Yeah. This is like the default model. This is sort of the vanilla model, if you like, where by specifying that model, we're saying all we care about is understanding if there's a difference between the low and the high settings for each factor. Does temperature, is there a difference between being set at a low temperature and a high temperature? And we're just going to assume there's just a linear relationship between them, and that's all we're going to test.
So because I'm not specifying anything other than my model / equation, we're just going to getting things at 2 levels. Because why would you do a third level if you're not asking for it? That's the idea here, right?
Yeah, exactly. If you only want to test these main effects, then the best experiment for that is just to have things at 2 levels, just at low and high.
Yeah.
If we think there might be some important curvilinear relationship with our factors, then we can't estimate that if we've only got a low and a high. We need points in the middle.
You're saying if we have something important there, right? And we have your temperature here, and you're testing that as a low and a high setting. All I can really do with 2 points are draw a straight line.
Correct.
Otherwise, we're not that artistic with the sign of experience. You really need that third point to see if there is a curve.
If there's a curvilinear relationship. Exactly.
And if there was a curve, like that would be a shame if you hadn't tested that point in the middle. All right.
Precisely. Yeah.
Good.
So quite often scientists and engineers want to test things at 3 levels because they are worried about that kind of situation.
And it's not that expensive. It's just so you see, if we were to run this, John will say you need 12. Could maybe sit to 9. Like I honestly say somewhere between 7 and 9 runs would be good for this design.
Yeah,
depending on
minimum. The minimum is always the number of parameters in the model. So we've got 1 intercept and 6 main effects. So we could do this in 7 runs. It's not recommended.
Cutting it short.
A default. Yeah. You want some extra runs to kind of test how good the model is, essentially.
First 2 X's here are the ones that I want to have at 3 levels.
Yep.
So to get them at 3 levels, I have to have them at powers second. And now I have them all at 3 levels. Then I had 2 of them I wanted to test at 4 levels. So is really a quadratic term is to the power of 2. And a cubic term would then be to the power of 3. Yeah. So I had to do this exercise one more time. And one way of doing it is just taking it there, like this is the x3, then selecting it from the list, and then cross it. And I get that cubic effect. It's probably not the smartest way of doing it, but it works.
It works fine, yeah.
I do it again for there, cross. So Phil, while I'm doing this, I just realized that I wanted to add blocking, or we were specifically asked to add blocking. And the way that I understand it now is I would normally have said, okay, I have a factor that was not easy to change. Like that's why I need blocking, so to say. And that would set my factor to a hard to change factor. But I hear you have some other takes on.
Well, So blocking, that is useful when there are factors, there are causes of variation outside of your control. So an example here might be, I'm going to run some of the runs. I'm going to execute some of the runs. You're going to execute some of the runs. And my dog Toby is going to execute some of the runs. So there's 3 experimenters here.
Okay.
And we've got a concern that maybe Toby, my dog, isn't very good at running these experiments. So he might achieve lower yields on average. And we know that Christian's really good in the lab. So Christian's going to achieve much higher yields, even though, that's a factor outside of our control. We don't particularly care about that factor. We know that Toby's a dog and he's not very good at running experiments. We know that Christian's amazing in the lab and he gets really good results. So that's an example where we'd want to block it because there's a factor there that is not within our control. It's not of interest to us, but we know that it can affect the results. So we're going to block it into, Christian's going to do 10 runs. I'm going to do 10 runs. Toby the dog's going to do 10 runs. But they're going to be set out in such a way that the effect of Christian, Phil, Toby is not confused with the things that we really care about.
I gotta say that's new to me, Phil. And that's like part of why you're here for me, and then we're just putting it on for everyone else to see if they benefit from that. No, that is interesting. Yeah, how would we even do that?
Well, you can add a blocking factor. So if you go to the add factor at the top, you can blocking.
Let's do 3 blocks. No, is that
well? So that would be 3 runs per block. So if we were going to do 30 runs in total, we'd end up with 10 blocks there.
So 10 runs per block.
Yeah.
All right.
Okay. We've got a blocking factor, and we could set those to Phil, Christian, Toby, for example, but you don't need to do that.
So it's only 1 and 2. So if I want to
if you scroll down a little bit and set the number of runs to 30.
Right.
Yeah, so now we've got 3.
Someone have thought about this at some point. Not me. Yeah. Like someone said, "Oh, this that was smart." No, let's do Toby. Is your dog actually called Toby?
Yeah. And he really isn't very good at running experiments in the lab.
And I have to say, I'm probably not very good at that either. No,
I'm not.
Last time I was in the experiment, I was trying to figure out how many C vitamins there was in a curly flower. And I was so bad at it that the chemistry teacher called me up while I was having dinner with my family out in a restaurant. Said, "Christian, you need to come back." It's 9 in the evening. Like, "Are you calling me now?" It's like, "Yeah." What you make no sense. So I had to come back, and so I was doing a report on this. So it was an experience. I failed chemistry. So I'm a mechanical engineer. If anyone should ask.
Well, there's a reason why I don't work in the lab these days as well. It was never my strong point.
I know. I found something that a term I really like. I'm a late bloomer. I got better with age, the kind of whiskey thing. Okay.
Yeah.
Okay, so we're back to square one but we've added one thing more. We've added that blockings that was being asked for.
Yeah.
And that person who sent me this has to come back to me and says whether he understood blocking my way or your way. But I really like this kind of blocking makes sense.
Good.
The way that I think about blocking sounds like whole blocks. Is that correct?
Yeah, so that's a different thing. So there's the idea of hard to change factors. So if temperature, if changing the oven temperature takes 2 days, then we don't want to change that between every run. So we say that's a hard to change thing.
Okay.
And then that results in what we call a split plot design. So we split it into whole plots, and within a whole plot, the hard to change factor doesn't change, and the easy to change factors do change. So that's a different thing from blocking.
Okay. So for me, that was blocking equals whole plots.
Right. It's a bit confusing.
We're just going to be moving on, Phil. We don't need to talk about it anymore.
Okay.
Cool. Okay. So we wanted to have x1 and x2 to the so all the continuous as a second level.
Right.
Then we wanted x3 add crossed one more time to get that cubic. And then we want x4.
You need to cross it with your quadratic. I think you crossed it with the main effect there.
Okay, and then, okay, so I take quadratic and main effect, and I cross it.
Yeah.
I take x4 and x4, cross it. One thing that's nice about this it really shows how custom it is. So if you have an idea, I have this really strong. So there was asked for some second order interactions. So I'm guessing that's because this person knows x1 and x3 are interacting. And some of the rest are probably not, but I want to make sure that my design is set up in such a way that I can see that interaction.
Yeah.
And I would say that's pretty common. When I talk to scientists, they've been on that machine for 20 years. They have a pretty good inclination of how things are going, but they want to get it in text or get it in statistics so they can tell the boss and say, here, what I've been saying for 20 years is correct.
Yeah.
Yeah.
Well, and I think the key message I would try to get across here is you should use all of your experience and understanding and build that into this design of experiments. So design of experiments is not a robotic, rigid, automated process. It's about enabling you to do the best experiments, enabling you to do better science, better engineering. So you need to bring all of your science and engineering experience, knowledge, even your intuition, just kind of your gut feeling from working on these things for however long you've been working on them, and bring that to what we're doing here in custom design.
Beautiful. So the last thing before we move on here is something that I'm a little confused about. And if I wanted to, I want really to be able to test all these interactions.
Right.
But would I need to add all of those second? Let's just try and do this. So if I only add
so
the ones
first of all,
I'm...
I think X7 is a blocking factor, so I don't think you want to do any interactions with that.
Yeah. But the rest
you might do, but let's not talk about that today.
But the rest there, if I were to add those as interactions second order, didn't actually add anything.
I think if you select them in the top.
Oh, here. So those ones and then interactions second. Okay, then I get up to 40. But do I really need all 40 to test all interactions? Or would some of them work?
Yeah, I mean, it's just a lot. It's just the nature of it when you've got a lot of factors. There's a lot of interactions between them because, X1 is potentially interacting with the 5 other factors.
Yeah.
And so on. So you just end up with a very large number. It quickly becomes a very big problem, right? And this isn't something that design of experiments, it's not a problem that design of experiments has created. It's just you've got a lot of factors. There's a lot potentially going on that you need to understand. And this just makes it very clear to you that you do. I mean, one of the things you can do is you could select all of those and then click on where it says necessary.
All right.
To the right, you can just click if possible.
Ah.
So it's no longer going to design an experiment where you can absolutely estimate all of these things, but if possible, it's going to give you the best chance of being able to estimate.
I like the if possible. We're gonna go with the if possible because this person said 30. So in this one, we're saying it's equally important for us to understand all of these interactions. So if I have some knowledge that this one in particular is really there, I could put that to necessary.
Totally.
Or this one is really necessary. I could put. So we've added all of them as if possible, and then you use your knowledge to say, no, these ones are definitely there. So I'm just going to add those as necessary, and that keeps us less than 30. We then specify it would be a good idea to do the 30 if we want to have as much possible runs to understand as many interactions as we can.
Right.
So since some manager can come and says you can do 30, we're going to do 30. Like that's
Yeah,
So
I mean, I think one thing to think about is whether you want to do all 30 in one go. I mean, let's assume we do in this case. We'll go with all 30 in one go. But I think something to think about more broadly is if the total number of runs that you can do is 30, maybe do 20 first, and then we can work out how best to use the remaining 10 later. But for this, let's just say, yeah, we're going to use all 30.
So coming back to the sequential idea we were talking about in the beginning.
Totally.
That sounds smart.
Yeah,
okay.
It is smart. Not my idea, but it's a smart idea.
All right, so we're gonna make the sign.
Sure. Let's see what happens. I mean, this is quite a complicated design. It might take Jump a little while to work out the best design for us.
And there. Okay, so the last thing that was asked about was power. Right. So we can see that in the power analysis.
And
that's a lot of numbers.
It's a lot of numbers, and a lot of them look very small to anybody that knows anything about power analysis. Especially some of these main effects. So my big thing here is you really need to understand what this power analysis is doing. There is this, if you read textbooks on DOE, you'll probably come across this idea that power should be greater than 0.8. And that's completely arbitrary. There's no reason why it has to be 0.8. But you need to understand what it means. And you need to understand that there's a lot of assumptions going into this calculation that may not be valid. Often, we don't have enough information to do a useful power analysis, right? So it's relying on, so first of all, you've got to decide your significance level, and you need to understand what that means. So you need to understand statistical hypothesis testing.
That's why we have comment sections, so people can ask questions.
Right, yeah. But let's forget about that. Put that to one side. There's two other key things that you need to understand to do a power analysis. The signal and the noise. So the noise, this anticipated root mean square error, that is essentially the standard deviation in the response that you'd expect. If you just ran the same settings 100 times, whatever your response is, let's say it's yield, what's the standard deviation? What's the typical variation of that from just running the same settings? So you need to know that. If you want to do a proper power analysis, you need to have a really good number of what that is. And then the other thing you need to know is the signal that you're trying to detect. And that's where the anticipated coefficients come in. And you need to understand what those mean.
Yeah.
Just going with the defaults is kind of meaningless. You can't, there's no point in saying I need a power of 0.8 if you're just going to use the standard defaults of the RMSE and the coefficients.
I think, Phil, for me, that was really interesting. I think let's gauge the response of the viewers to see if they want more words on this. I feel very blessed to have to pick your brains on this because I felt that was difficult to explain.
My advice is don't worry about power analysis.
Okay.
Essentially, it's not the most important thing right now, I think, when you're first starting to understand DOE.
Another takeaway I have here is that if we were to run this just ignoring the power analysis and we did not get any good p-values, we could add some runs by augmenting this design. So this is not a one-off. This is an off. And you could do this again. Like you could add more runs to this, and that would improve your power, right? So it's not a static number, I should say. And if this one is really, like we set this to 5, look at that. It has a great power. So again, there's a lot of things that we could be talking about here, but let's say that this is a good design for what was being sent to us. It answers those questions, or it definitely would give a lot of insight to those questions. And if we had make the sign, I'm happy with suggesting this person to run with this. What do you think?
Yeah, I think so.
With the information we have at hand, right?
Exactly. Yeah, I would want to ask a lot more questions.
Yes.
Think hard before you start is good advice when you're doing design of experiments. Really understand what it is you're trying to do, and then.
Would you say is it easier to add a new factor in the beginning of the design of experiment or in the end?
in the beginning is
So
the
when you're
standard
already done,
advice
it's,
is yeah.
yeah.
Start with a large number of factors. We can run a screening design to see what's important, and then we can narrow it down and focus on the most important things in the next bit.
Bill, thank you so much. I think that was a lot of really good tips and tricks and insights. And
good. Thanks, Christian. It was a lot of fun.